What you're starting to allude to there is this idea that like something that's a characteristic of transformer-based architectures is that they tend to be densely activated. So you're activating either all of the neurons, or more recently it's become in vogue to kind of have modules of neurons, but then you still have dense activation within those modules. And when I say dense, I mean that you're flowing information through all of the neurons in the network or all of the neurons in that module. And this is computationally expensive, energy expensive. If the human brain were to do that with the trillion connections that we have in it, we wouldn't have enough energy to support that. And so we have a much sparser activation system in our brain, in the human brain, which is that, so only, a relatively small portion of neurons are being activated at any one time. And there's all kinds of things. So then you can do things like functional magnetic resonance imaging, fMRI studies, or EEG, electroencephalogram studies, to be able to see what parts of the brain are active during particular types of thought. And that you can do that is demonstrative of the fact that we have a sparsely activated brain. And so a big thing that you've done with BDH is that this now allows for sparse activation. So you can correct me if I'm wrong on the stat, but it looks like 95% of the artificial neurons in BDH are silent at any given time. They're not firing. And yet the model is able to rival. So right now you've only been experimenting with it being a little baby dragon hatchling. So it's a relatively small network. It's about 1 billion parameters, which is about comparable to GPT-2. GPT-2 is densely activated. So all of the neurons are being activated at any given time to any given prompt. Whereas in yours, only about 5% are active at that time, much more like a brain. Maybe explain a bit more about that and how central that efficiency principle is to BDH, as well as the implications for biological brains.
Absolutely. So, John, indeed, the idea of working with models at a billion parameter scale here is largely for the sake of demonstration of certain tasks that we can work with. And here we were really looking at the core tasks that can be considered advanced from the point of view of cognition, related to language, related to translation, of tasks that need attention. We are demonstrating it at this scale. Indeed, the aspect of sparse activation is a fascinating one. It's an aspect which is it's quite deep because there's a bit of a chicken and egg story to unravel here. In fact, there are two worlds which work well, which can be compared to each other. However, there's a gap between them. So there's no middle ground. You can be in one world or the other world. One world is the world of dense activations, which is the world the transformer is in. The other world is the world of sparse positive activations. This is the world that Baby Dragon Hatchling is in. Incidentally, the use of sparse positive activations in biologically inspired models and their discovery in brain function is a topic which has been ongoing at least since the 90s, with brilliant work regarding visual function, olfactory function, basically sense of smell, even for the fruit fly, which relies on sparse positive activation. So these topics have been explored from the point of view of their presence in the brain. But the use of sparse positive activation for reasoning is something that's new. We believe we are the first work that has actually scaled it to transformer-like or beyond transformer performance. And the fact that we are at 1 billion means it scales onwards, meaning all the key points have been achieved and we have achieved the scale. The implementation is GPU efficient, by the way. So just to reassure everyone there's no, especially for infants, it has a lot of points which allow us to outperform the transformer on certain hardware configurations quite significantly. So this is actually super encouraging. But maybe one more thing to say while introducing the topic, and maybe we can dive in just a little bit on the technical side what these two worlds mean. But there's one main difference between the two worlds, which I'd like to kind of highlight.
Yeah, and so just kind of recap those two worlds. So on the one hand, you have the densely activated world of the transformer, where, as I was talking about earlier, when any prompt goes through in a fully dense network like GPT-2, all of the neurons, we run compute through every single neuron, every single connection on every input that goes into the model. Whereas the other world is the world that the baby dragon hatchling, BDH, lives in, where some small percentage are activated.
So I would say to analyze the transformer, you can actually dive deeper, because for the transformer, essentially, if you look at the architecture which is behind the transformer, and for most open source models, the basic part is the GPT-2 architecture. Nothing much has changed really. If you look at all the family of Llama models, Llama 3, Llama 4, all of them, this is like GPT-2, almost unchanged.
Yeah, just scaled up.
Just scaled up. So here, the scaling of the transformer is actually a bit of an interesting story, because there's no like one single recipe for scaling the transformer. It ends up being done differently. You have a different number of attention heads, you have a different number of layers, etc., etc., etc. So the transformer scales in different ways, and it's a little bit of know-how how to scale it, or actually, it's from the point of view of a theoretician, or somebody who would want to apply something like computational complexity and ask what's the limit of a transformer. It's actually rather hard to decide how we should scale it up. But there's one dimension which appears to be fixed, to have converged, and that's the size of the attention head vector dimension in a transformer. So this does not scale even as the models get larger. It has stopped scaling, and here the intuition is that basically all concepts that the transformer works with have to be mapped into a vector space of about 1,000 dimensions.
I see.
Yeah.
So we have this constraint that's appeared in the transformer that will limit its ability to have nuanced reasoning, because it doesn't seem like we can scale the dimensionality of the vector space of the attention heads beyond 1,000.
So this is actually a point that we address a bit more mathematically in our paper, because we take the opportunity to analyze both, baby dragon hatchling, and also kind of take the reverse approach to history and look at transformer as an approximation of baby dragon hatchling, because it's actually easier to take this direction to say that we're coming up with a simpler and somewhat cleaner mathematically architecture, cleaner in terms of the number of moving blocks. So here the advantages, we can kind of look back at what the transformer is doing from this perspective, and somehow see the way it organizes concepts and maps them into a vector space. The kind of question which comes up, and this is, I think, for a large part of the audience who are familiar with vectors, with vector spaces, with notions even quite far from the transformers, such as let's say preference vectors, you can manipulate them as if it was a linear space. So you can add vectors together, you can subtract vectors, you can have the opposite elements, you can have a negative vector, and this is the essence of a vector space. By contrast, if you go into the sparse positive spaces, the way you actually compose concepts is somewhat different. You don't work so much with linear combinations of vectors. You work more with bags of concepts, so bags of words, combinations. It works a bit like a tag cloud. It looks a bit like an association set, so a number of elements put together which form a whole. It's a bit how you form sentences by putting together words to get the meaning correctly, or in some languages which have a bit more of a tendency to play, especially Germanic languages, German in particular, where you compose multiple words to create a new noun, for example. This is a place where you have this kind of compositional effect, and there are a number of differences. One difference to this type of representation, apart from like the points that you discussed, John, about efficiency and so on, is actually that you don't look so much towards negatives or opposites. Starting with a simple example, if you show somebody a piece of work that's been done badly, and you tell them, look, this is what you're supposed to do, but do the opposite to get a good effect. There's no such thing as take the opposite and find, the opposite to it. Likewise, we don't like in reasoning patterns. There's no symmetry between being attracted towards a certain reasoning pattern and being repelled from it. So if I tell you now, don't think about the color blue, you'll be consciously thinking about the color blue just to try to compensate for it and avoid it. But it's not the mechanism of switching off, of damping down. So we are in a different vector space, in a different space.